Hello, everyone. My name is Shigang Liu. I'm happy to present our paper titled EaTVul, ChatGPT-based Evasion attack against the software vulnerability detection. This is a collaboration work among CSIRO's Data 61, Swinburne University of Technology, and the Defense Science and Technology Group, Australia. Let's begin with some background on machine learning for software security. As we know, machine learning as a service has been widely applied for cybersecurity, especially in software security. For example, Amazon Web Services offers Code Glue Reviewer, which is a machine learning-based developer tool that helps to detect critical issues and security vulnerabilities. However, it is well known that adversarial learning has become a significant threat to cybersecurity, and there is a lack of research on adversarial learning in software security. Here is a motivation example. On the left-hand side, we can see this is a vulnerable function, and a machine learning model predicts it as a vulnerable with a very high probability of 93.2%. However, after we insert a well-prepared adversary dart, we can see in the red box, then this vulnerable function is predicted as a benign function with very high probability of 87.4%. So this motivates us to conduct fundamental research on evasion attacks to gain a thorough understanding of the security issues in machine learning-based software vulnerability detection. So in this work, we will explore the vulnerability of machine learning models to adversary attacks. At a high level, our aim is to develop an effective scheme for generating adversarial code capable of misleading the machine learning-based software vulnerability detection systems. So the assumption in this work is that we assume the attacker can perturb the test queries. And we also assume the attackers lack access to the architecture and parameter of the target models, but they can get all the open resources, such as they can download all the dataset from NVD. And the attacker's objective is to deceive the vulnerability detection tools through the modification on to the input. So now let's have a look at the proposed scheme. So the proposed scheme consists of two stages. So the first stage, we can see the number one on top of the arrows is the adversary data generation process, and the second stage is the adversary learning. You can see the number two on top of the arrows. So in the first stage, we first use the we first identify the support vectors of not vulnerable samples by using support vector machine, and then all these samples will be used as the input, and then we use attention mechanism to identify the features that contribute the most to the prediction. After that, we use GPT to generate the adversary dart. So the input are the prompt and the attention word, and the output. Okay. So the output include the adversary data we call original adversary data. Then we use GPT to further optimize the data. We call it optimized data. And in the second stage, we use the fuzzy genetic algorithm to automatically choose the seed attack examples from the preserved attack pool, and then to launch the attack. For example, giving a vulnerable example, after we insert the well-prepared adversary data, the prediction result will be benign. Here is an example of the features identified by the attention mechanism. In this example, the identified features include the static constraint string and so on, and the importance decreasing from red to yellow. And these features will be incorporated into the generation of adversary data. So here is the example of the original generated code snippet and the optimized code. On the left-hand side, we can see there are many lines. And so we call this original generated code snippet. And however, to maintain the stealthiness, the size of adversary data will be limited to no more than 8 lines. So we use GPT to further optimize the adversary data. On the left-hand side, we can see the optimized code snippet. So here is a visualization of the movement of the vulnerable samples after inserting the well-prepared adversary data. As we can see from the left figure, the vulnerable and non-vulnerable samples are displayed on either side of the decision boundary. However, the figure on the right shows some of the vulnerable samples are classified as not vulnerable, as identified by the red box. So after inserting the well-prepared adversary data. So here comes to the evaluation. We will answer the following 6 questions to assess the effectiveness of our proposed scheme. Actually, the experiment result shows that our proposed EaTVul performs the best in all scenarios. Specifically, research question 1 demonstrated that using fuzzy genetic algorithm to select the seed adversary data for launching attacks outperforms random selection. Research question 2 shows that using optimized adversary data outperforms using the original generated data. And then research question 3 assesses the effectiveness of the proposed EaTVul attack against traditional machine learning techniques. And research question 2 evaluates the effectiveness of the proposed EaTVul against the deep neural networks techniques. And research question 5 indicates that our proposed EaTVul outperforms other attack models such as obfuscation method. And finally, research question 6 provide the generalization of our proposed scheme by using Java language. So research question 1 to research question 5 are mainly using the C and C++ language, and then we move to research question 6 using Java programming language. But due to time limitation, I will focus on research question 5, research question 4, 5, and 6 as an example. So here is the result for research question 4. So this result shows the effectiveness of the proposed EaTVul against the 4 victim models. Taking the large language model code Zhang as an example, our proposed scheme can achieve more than 89% successful attack success rate with top 5 and top 10, and 7% and 88% attack successful rate with top 20. So when the code snippet size is 2 and 3, the code snippet size of 2 mean, so there are 2 pieces of code snippet will be selected as adversary dot. Similarly, we can see that our proposed EaTVul outperforms both the obfuscator models and the middle model in terms of victim models as Adversarial and EaTVul. In this table, the F1 score represents the performance of the victim model before the attack. So a high F1 score indicates that all the victim model performed well before attack, and we can see EaTVul still achieved a very high attack success rate with more than 84% in all cases. Research question 6, we can see the target model are Adversarial and EaTVul. And in this experiment, we are using Java programming language. These methods are representative techniques. They use different ways of programming representation. Both have shown to have very high precision in detecting software vulnerability detection. We can see our proposed scheme performs the best. So this again emphasizes the generalization of our proposed scheme. So in conclusion, we have proposed a novel evasion attack scheme targeting machine learning and deep neural network models for software security. And our experimental results demonstrate the effectiveness of our proposed scheme. We have also open sourced the code to encourage further research and development. Moreover, our findings demonstrated that there is a strong demand for developing robust defense mechanisms in software security. Of course, there are some limitations. For example, we propose a attack strategy, but we haven't proposed the mitigation, and that's one thing. And others can be like make an improvement using other method for attention for the important features identification. We are using attention mechanism, but could be consider other techniques such as sharp. Yeah. That concludes my presentation. Thank you for your attention. I'm happy to take any questions. Thank you.